Right now, SpaceX is hiring engineers to design data centers for orbit. Axiom Space already has a prototype sitting on the International Space Station, and early satellites have been launched to test high-performance AI chips in low Earth orbit. Just getting hardware off the ground requires an immense amount of brute force. Earth's gravity well demands thousands of gallons of rocket propellant to lift even a modest payload into the atmosphere. And once it gets there, the environment is actively hostile. Launch costs are high. Solar radiation degrades microchips over time. And if a server blade breaks, you cannot simply send a technician down the hall to swap it out. But the most difficult engineering hurdle is temperature. Computers generate heat. On Earth, we use moving air or chilled water to carry that heat away. In the vacuum of space, neither of those options exists. So, if placing a delicate computer in orbit currently makes zero financial or engineering sense, why are credible companies and governments investing in it anyway? This investment points to a massive structural pressure back on the surface. We are beginning to see the absolute physical energy limits required to sustain the explosive growth of artificial intelligence. For years, the digital economy felt detached from physical constraints. We use terms like the cloud as if software and data were weightless and intangible. Artificial intelligence has changed that perception. Data centers are not just warehouses for information. They are energy conversion facilities. They transform raw electricity into computation while managing the massive thermal load that results. This animation illustrates a basic law of physics, entropy. Every single computation increases entropy, and every increase in entropy produces heat. If that heat cannot be dissipated, the hardware's performance degrades. We have industrialized intelligence, and industrial processes are governed by energy. If heat cannot be carried away, the entire system breaks down. This isn't a design flaw, it is an unavoidable consequence of processing information. Artificial intelligence is a physical process, and like any other industry, it is strictly bound by the laws of thermodynamics. Earth can certainly power AI. Renewable capacity is expanding, nuclear power provides stable baseload energy, and fusion research continues. The issue is timing. Building a physical power plant involves years of planning, permitting, and construction. AI capability improves at a much faster rate through continuous research and hardware scaling. Additionally, electricity for large AI data centers must coexist with residential demand, manufacturing, and climate transition goals. Clean energy is a finite resource that must be distributed across these competing priorities. So, if terrestrial infrastructure is slow to build and the current grid is under pressure, where is the one domain with no clouds, no night cycles, and no competition for land? The growth of AI is significant enough that researchers are exploring additional energy domains beyond the terrestrial grid just to maintain momentum. This is the appeal of low Earth orbit, up to 2,000 kilometers above the surface. Here, solar energy is near continuous. In orbit, you co-locate generation and computation. Solar arrays sit directly beside servers, reducing the strain on terrestrial power systems. We still have to address the cooling problem. Without air, heat must be emitted outward as infrared radiation. This requires an enormous surface area of radiator panels, which adds significant mass and complexity to the structure. The physics of this are already proven. Systems like the International Space Station use radiators and heat pipes to regulate their temperature in a vacuum. While the physics work at a small scale, scaling this to gigawatt-level infrastructure remains an unproven economic challenge. For now, it is a test of feasibility rather than a deployed alternative to Earth-based data centers. In 1964, Nikolai Kardashev proposed measuring civilizations by the energy they harness. Humanity has not reached Type 1 status, capturing all available planetary energy. AI makes this concrete, exposing the energy envelope within which it operates. Orbital computing is an experiment in expanding that envelope. Compute capacity now directly influences major scientific advancement and our global defense systems. Because this capacity is limited by energy, access to resilient and expandable power systems has become strategically significant. Entities experimenting with orbital computing are not predicting it will dominate. They are hedging against constraint. It is a sign that energy strategy and AI strategy are beginning to converge. Ultimately, this push for orbital computing is less about leaving Earth and more about understanding the absolute limits of scaled intelligence. It asks a profound question. How far are we willing to expand our infrastructure to sustain these energy-intensive systems? The push for space is evidence that AI is pressing against our existing energy frameworks. To understand the physics, the economics, and the strategic stakes of this new frontier, read Ritesh Menon's full essay linked below.